Recording is rolling. It's Friday, May 15th. We're gonna finish the stats packet. So it's in three parts, part A and part B. We did the last couple of days. We're gonna do part C, and then that'll close this. Then you guys can turn this packet in. Okay, so here's a review of some of the main concepts you guys seen so far. Of course, this is obviously not an entire stat class. We're just doing 3 days, but it'll introduce you to some of the main important ideas, and then hopefully some of you guys do take stats one day. Maybe you need it for major, or maybe you just take it for fun, because yeah, I think there's a lot to get out of something like this. Okay? But we've been looking at examples of either heights of dogs, cats, or people, or there was an example with like how much liquid is there in a bottle. Say if you have like a whole factory line of bottles and it's filling up, there's like some plus or minus factor. You can make a histogram for these values. So say if I was looking at heights of dogs, you could have short dogs, and maybe there's only a few short dogs. There's a lot of medium-sized dogs, and there's only a few tall dogs. And then instead of having a histogram of a bunch of bars, like a bar chart, you can stand back, look at it, and this bell curve will emerge. Okay? Now, not all data in the world is distributed normally. This is called normal distribution. Actually, height might not even be a great example, but a lot of data is, just to get this idea on the board, right? Okay. And then we're saying, to this inflection point here, where it switches concavity from concave down middle to concave up on the tails. Well, that's an inflection point, and the distance from the mean to the inflection point is called the standard deviation. I gave you guys formulas to find the mean, average, and the standard deviation. And going from the mean plus or minus one standard deviation, as long as your data is normally distributed, which again, a lot of data in the world is, that should cover 68% of all the population. Okay, so approximately 2/3. Okay, and then you have approximately 1/6 is in this tail on the right, and the other 1/6 is on this tail on the left. Okay, and then yeah, I think it's about where we are. Okay, so you guys do a recap. All right, so let's look at part C. Now, what's new about part C is we're going to put examples into groups. So start grouping these. And so here's some familiar formulas. You guys know mean average, standard deviation, walk through with you guys. Okay. Here's Z-score. So for an individual, you can get a count of how many standard deviations above or below the mean. Here's what's new for this page right here, is if you start putting samples into a group. Right? So I'm saying take the regular standard deviation, say for individual population at large, divide by the square root of the sample size, and that'll tell you the standard deviation expected for that group. Right? And if you have a really big group, like say if n was a billion, well, you'd be divided by a huge number, and it looks like the standard deviation would be closing down to zero. Right? Guys, think of it this way: if I said like, what's the height of an individual person? Like, what's the height of the next person that walks in the door? Yeah, maybe they're 5'5" or 5'9" or 6'5", right? I mean, any of those are possible. There's no probability associated with that. Right? But if I said, oh, like the entire world population walks in through the door, like all 8 billion people, or however many there are, 8 billion people, okay, then wouldn't it necessarily be the case that the average height of that group matches the average height of the entire population of the world? Because it'd be the same number at that point, wouldn't it? Right. So then there would be no more variability. Right? There would be no more question. Okay. And how this actually ties to quantum mechanics that you get. You guys did turn in the journal for quantum mechanics. Right? I got it for most of you guys. If you haven't turned in your journal yet, then turn that in, and I can grade that, give that to you guys. But how this relates is when particle physicists are smashing atoms together over at Large Hadron Collider, for example, or these particle colliders, and they're collecting the statistical data about mass, charge, and spin. They can't make any definitive conclusion from any one collision, but what they can do is they can group together to like millions or billions of collisions and make some conclusion statistically based on that. Okay, so let's get a more down to earth type example. Right, so we're back to height. Suppose the average human height is so many centimeters. Again, this is where we all have different versions. So my version is probably different than yours. Right? So my height says 174 centimeters on average. You guys remember yesterday, we took meter six and we're measuring each other's heights. So I have an idea. Okay? You know what your height is. Okay? And let's throw a standard deviation on this. Standard deviation. Now my standard deviation says 7 centimeters. So I could say, like, if this data was true for the world, if I do 174 centimeters plus or minus 7 centimeters, that should cover 68% of all people, right? Because that would be the average plus or minus one standard deviation, right? So that should cover about 2/3 of all people, if that was true. Okay. So let's go through these questions here. First question, what's the expected value of height for the next person who walks through the door? Expected value, right? Well, it could be anybody. So if you go, let's say incremental, like to the nearest centimeter, guys, what's probably the best number you could put here? Yeah, how about the average? Because whatever your average is, just go ahead and copy paste that number right here. Now, since mine's 174, I write 174. Yours is probably a little bit different number. Okay. You guys know how to find that? So expected value, just in general, or I don't know, I'm just gonna put the average. That's incrementally probably the best if you do anyway. Hey, and what's the standard deviation for, again, just an individual person who walks through the door? Well, I'm just gonna copy paste the standard deviation right here. Okay. So that's my plus minus factor to cover that. So this average plus or minus this standard deviation should cover 68% of cases. Okay. Or maybe I get someone who's frequently tall or short, maybe outside that range. Okay. Therefore, what's the percentage chance that next person walks in the door has a height greater than or equal to this very, very tall height here? Okay. And I tell you how to find, or I remind you guys here in parentheses to say, get a z-score and then consult the z-table. You guys remember you have this z-table on the back of the packet? Okay. So I'm going to run my numbers, and then you guys run your numbers, so that when you turn this in and I check my grading key, then you'll have the correct value in place. So remember what z-score is. It's the number of standard deviations from the mean for an individual. In our case, okay. If it's positive, it's above average, and if it's negative, it's below average. Okay. I mean, if you understand that concept, then you probably know how to put this equation together. Right. So I'm going to take the individual value, subtract the mean, and divide by the standard deviation. So it's some version like that. Or you might see it this way. You might see individual value. The mean sometimes is written like this, and the standard deviation is sometimes written like this. Okay, so okay. So let's see. So I'm looking at a target value of 180 centimeters. I said that, at least in my world, on my paper, the average height is 174 centimeters. And the standard deviation, that plus or minus value, was 7 centimeters. Of course, your numbers are probably different. So, okay, so don't copy my numbers strictly, but they should be fairly similar, like in that ballpark. Let's get a z-score here. So a super tall person minus the average, put that in parentheses, and then divide by standard deviation size. I'm getting a z-score of, well, I'll round to the nearest hundreds, because that's as good as I can do on the table anyway. Okay. So there's my z-score for a very tall person. Did you guys get a z-score for your very tall, or well, whoever, tall, short, whatever your numbers are? Do you guys have a z-score? Okay. That's going to go right here. So there's my z-score. Bam. Okay, you guys got a z-score? And if you did it correctly, you should get something between about -3 and 3. Okay, you guys remember that too. Is remember that once you get to like 3 standard deviations beyond the mean, you're really extreme far out on the tail. I mean, if you're 3 standard deviations taller than average, you're probably like 7 feet tall at that point, or getting pretty close. Okay. Okay. All right, so you guys get it. You guys get it. Okay. Now we need to apply the z-score and get the percentage. And look how the question is framed. Is the question framed how many people are shorter or how many people are taller? Yeah, how many people would be taller according to this, right? Have a greater height would be taller, right? Which means that you're not actually looking at the shaded region on this bell curve. You're looking for this tail to the right of that. So I have to subtract from 1. Okay? Okay. So for example, here my z-score was 0.86. So here's 0.8, 0.80, 81, 2, 3, 4, 5, 6. Okay. Remember, go across the you guys see it going across the columns. You can go to the hundreds place. So here's a z-score of 0.86. Okay. And the decimal reading, if I can get this to not be blurry, is it says 0.8051. I'm going to round that to 81%. Is that okay if I round that to 81%? Okay. Now, guys, there's still one more thing I got to do. Is if this shaded region represents 81% of people, then this tail over here on the right is how many percent? Here, okay. Pretty close. Yeah, pretty close. Yeah. All right. So here, let's go through the whole process again. So I got a z-score of 0.86. It's positive. That means this person's taller than average. I figured that anyway. So here's 0.8, and then go all the way over to 6. Here's for a z-score of 0.86. And what numbers does it say? It says 0.8051. So I'm going to round that to 81%. Okay, 81%. Okay. Now, there are 100% of people in the world. Subtract off the 81% of people who are shorter than this particular individual, because that's what corresponds to the shaded and part of the bell curve. Okay. And that leaves me with 19% would be taller than this person. Right. So I can go to right here, and I'll say there are 19% of people who are taller. Yeah, we all have different numbers, but that should model the same process that you guys are doing. Okay, so if you kept up with me, you should have the first 4 boxes filled on this page. Okay. Does anybody not have the first 4 boxes filled? Okay, so everybody's good so far? Okay. All right. All right, so actually nothing new so far. What we've done is the same things we've doing for the last couple of days. Okay. But number 2, right, here's where there's going to be this new application. We're going to start putting people in groups. It says, what's the expected value for the next 5 people who walk in the door? Okay. And actually, guys, what do you think is a good expected value for a group of 5 people? Should be the same number as before. So I can just copy paste that again. That doesn't change. Okay. But remember a few minutes ago I said if you let all 8 billion people walk in through the door, at that point the average of that particular group happens to match the average of everybody in the world because it's the same set. Okay. So there would be no variability at that point. So what we're going to do is say we're going to apply this right here. It says sigma for group is sigma for an individual divided by the square root of the group size. So I'm going to go, all right, so okay. Sigma for 5 people is sigma for 1 person divided by the square root of the group size. So for me, I know that my plus minus value was 7 centimeters. That was my standard deviation for population at large for 1 individual. Okay. But I'm going to put them into a group of 5. So I'm going to divide by the square root of 5. And that's going to give me a much smaller standard deviation. But 7 over the root 5. Okay. It's like 3.13. And then the unit would still be centimeters. It's still a standard deviation. But now it's for a group of 5. Is there any questions so far? See, especially conceptually, why the standard deviation would decrease if you have a group of people. And the larger the group, the less the variability is going to be. Okay? Like if I had a group of 100 people, guys, what's the square root of 100? It would be 10, and then 7 divided by 10, that'd be like 0.7. Right? So, okay, so now that standard deviation would be getting really small. Okay? Because the larger the group, I know that the average of the group is going to tend towards the average of the population in general. Okay. There's a name for that too, and stats. I forget what it's called, but some very basic theorem. Okay. So I got 3.13 centimeters right here. Okay. Now, if you're doing everything correctly, then here's one important feature to look for. Your standard deviation for the group has to be smaller than it was for a single individual. Like for me, 3 is less than 7. Okay. Are you guys also getting that? Okay. Oh yeah. I think that's okay, so take your standard deviation, which I gave you right here. Okay. Divide by the square root of 5. And that's it. Okay. Is it? Therefore, what's the percentage chance that the average height of a group of 5 people is greater than or equal to, hey, look, 180 centimeters. That's the same height mark I was looking at before. You see that 180 matches that 180? Okay. Now again, you guys have different numbers than I do. But these 2 boxes should match each other, whatever they are. Okay? Like maybe yours says 185 and 185 or whatever. Okay? I have 180, 180. Okay. What I'm trying to say is that before the probability that, let's say 180 is like the cutoff for a very tall person. Okay? The chance that a very tall person walks in through the door is only 19%. But, okay, so we have a group of 5 people. What's the chance that on average, the average, or I should say, the average height of an entire group of people is also very tall. Is it going to be also 19%, or is it going to be much smaller than 19%? Yeah, it's got to be a lot smaller, right? So let's try this out. So what's Z for this group of people now? So Z is, let's take the target value of, well, for me it's 180 centimeters. I subtract the average. Okay, so far it's looking the same as before, but now I have a much smaller standard deviation size. So let's go to Z here. That's a much larger Z-score. Much larger Z-score than before. Yeah, I think this is all corresponding. So go write my new Z-score. Yeah. Okay. Yeah, if I compare my Z-scores, before I got some Z-score, it's kind of get up there, almost one standard deviation. But now for a group of people to all collectively be very tall, a lot less likely to be a lot further out on that bell curve tail. The Z-score must be much bigger than before. Are you guys, for your paper and your numbers, also getting a Z-score that's bigger than it was before? Because if you are, you're probably doing this correctly. Okay? You guys good so far? Right. Now, to seal the deal here, what's the likelihood that, again, group of 5 people are collectively very tall? I think this probability is going to be very small, but let's find out for sure. So I go to my Z table. I know my Z-score is 1.92. So here's 1.9, 1.90, 1, 2. Okay, so I'm pointing at the probability right here. So here's the Z-score 1.9 and then 2, so 1.92. Okay. It says, or 0.9726, I'm going to round that to just 0.97, as in 97%. Okay? Now, remember what that means in the context of this bell curve. I'm saying that 97% of groups of people would collectively be shorter than this tall value. Okay? Guys, if 97% of groups are shorter, then what percent of groups would be taller? 3. Yeah. So that is the answer. It'd be 3%. Okay. So to recap this in, I think you guys got this, but just to really, really hammer this in. Okay. The chance that a very tall person in a single individual walks through the doors, let's call it about 19%. But if a whole group of 5 people walks through the door, and I measure all their heights and take an average, and on average they also turn out to be very tall, well, that hardly ever happens. It's not impossible, but it's much, much less likely. Right? Guys, I did? Right. Now, here, while you guys are digesting this a little bit, there's always a story attached to this too, because it also relates to the particle physics and quantum mechanics. Okay? So, the analogous story here is, say we're a bunch of aliens in a spacecraft, and we're hovering around Earth in our flying saucer, looking down. Okay, and we're trying to learn something about human society, and one observation somebody makes is like, it looks like we have these giant auditoriums. We don't know what's inside. We can't see inside the auditorium, but we do see regularly groups of very tall people walking in. And it's like they're like 7 feet tall, 7'5", and they're looking like in groups of 5. Right? And so we start hypothesizing, like, why could this possibly be? Why is it that there are consistently groups of 5 very, very tall people walking in these auditoriums and we can't see inside? Right? Okay. And finally, somebody comes up with a hypothesis. I think that there's this game I'm going to call basketball, and we don't know exactly how it works, but we think that the rules are such that you would have an advantage playing this particular game if you were very tall, and they're probably in teams of 5. Okay. And now we need to put this to the test. So, if you could show that this was consistently the case, where there are auditoriums all over the place, and you have teams of very tall people, and there are groups of 5, okay? How does it? And that's sort of analogous to trying to find out, does some particular particle exist in quantum mechanics? Does the Higgs boson exist? Or does it have these certain mass, charge, and spin properties? Right? And if you can say, well, if a team of, let's say a group of 5 people who are like 7 foot tall, right? For them to randomly show up in the world, there'd be almost zero chance of that happening at all. Right? But if this particular game called basketball exists, and I think it has sort of rules like this that work this way, that would give this advantage, right? Then you would expect very tall people to show up in groups regularly, walking into these auditoriums, because that would be consistent with that particular game. Right? Okay? And then you would be able to statistically confirm the existence of a game called basketball. Okay. All right, so here's one more story example here, and we're going back to filling bottles with water. So again, we're going back to this factory line. If we got this row of bottles and fill with water, bloop, next, bloop, next, bloop, next, bloop, next. Okay. But there's going to be a little bit of a plus or minus factor. And maybe you are a government agent, but maybe it's some consumer protection agency or something, and you want to pull a bunch of bottles off the shelf and see is there truth in advertising. So maybe like I look at it here about bottles of water that are like 1,001 milliliters. Right? So okay, so maybe they're advertising got 1 liter bottles, 1 liter, which would correspond to 1,000 milliliters. Okay. You know, saying I wonder if that's true. Are they really filling these bottles with 1 liter of water, or are they shortchanging all their customers and they're really putting in 950 milliliters? So we're going to grab a bunch of bottles off the shelf and we're going to crunch some data and see is there truth in this advertising. And by getting bottles in groups, a whole group of bottles, then you can have a better, more definitive sense statistically than if you just grab one off the shelf. Right? So here's what we did. For this number 3 and this number 4 here, the story of filling bottles with water, I will leave that to you guys. And yeah, and the rest of the class. And I'll walk around and help you guys out. When you finish those, you can turn those into the great tray.